Folks, this is dull and it has a tremendous mass. The fact that 3 conclusive pieces of evidence make what more? It's little. Not too far off, right? Embroiling a super-gigantic dark opening space can be alarming. To ponder the perils that prowl inside the immense field of room can be frightening. While this applies to the whole idea of room investigation, the one section that has forever been captivating and unnerving simultaneously is dark openings. These monsters of force have been the subject of endless examination all across the globe. Researchers have been attempting to sort out exactly what dark openings truly and exist in them. Yet each of that changes now. Neil deGrasse Tyson recently uncovered something enormous. Our dark opening is less huge than the one in the focal point of the Andromeda cosmic system, our closest huge world. So we have dark opening jealousy? I figure we do. We at last see what's inside a dark opening, and, well, every last bit of it may very well knock your socks off. So, go along with us as we take you on this intergalactic excursion and respond to one of history's most posed inquiries. What is a dark opening? Made from a huge blast, the dark opening's mass is packed in a staggeringly little district, creating a gravitational force so serious that nothing, not even light, would be able to escape from it. Once something is in there, remaining in there is going perpetually. These forces of energy come in different sizes, ranging from heavenly dark openings, which can be a couple of times the mass of the sun, to very huge ones that exist at the focuses of systems and can have millions or even billions of times the mass of our sun. Scientists have noticed the impacts of dark openings by implication throughout recent decades, and with each piece of information we uncover, hundreds of privileged insights arise. Despite the fact that it appears like they're so enormous and strong that they couldn't really have a beginning story, they really do. Dark openings don't simply exist in space. They're made. They need the remainders of huge stars that have depleted their atomic fuel to be conceived. These stars go through a cosmic explosion blast, a dynamite occasion that imprints the finish of their lives. During a cosmic explosion, the external layers of the star are fiercely removed into space, while the core undergoes a gravitational breakdown. Not all breakdowns are something similar. If the core's mass is a few times bigger than that of our sun, the force of gravity overpowers any remaining forces, making the core collapse inward. This breakdown is serious to the point that it packs the mass into an incredibly little volume, creating an object with a gravitational field so strong that nothing will actually want to get away from its grip, thus creating a dark opening. The size of a dark opening is determined by its mass. Heavenly dark openings, which are the most regularly realized type, have a mass range from a couple of times to many times that of our sun. At the core of a dark opening lies the peculiarity, a region of endless thickness and spacetime curvature. According to our current understanding of physics, the laws of nature break down at this point, and our regular theories can't fully explain what happens inside the peculiarity. To truly grasp the concept of singularities, we need to think outside the box in the universe of physics. A peculiarity refers to a point in spacetime where certain quantities become endless or indistinct. These singularities show up in various theoretical settings, for example, at the beginning of an expanding universe, commonly known as the Big Bang peculiarity, and inside dark openings. When we study the Big Bang peculiarity, a central challenge arises. According to the theory, the universe began from an incredibly hot and dense state around 13.8 billion years ago. But as we rewind time toward this initial state, the conditions of general relativity, which govern the behavior of gravity, break down. This breakdown implies that our current understanding of physics can't fully describe the conditions at the moment of the Big Bang. Solving this issue requires a theory that combines general relativity with the principles of quantum mechanics. Dark openings contain peculiarity at their centers. These are regions where the gravitational pull becomes infinitely strong, and spacetime is deeply curved. According to general relativity, matter and energy that fall into a dark opening reach its peculiarity and become infinitely compressed. This concept is beyond our current understanding of physics. Adding to the problem, the challenge of singularities has spurred scientists to seek a theory of quantum gravity, which aims to unify the principles of general relativity and quantum mechanics. Quantum gravity seeks to provide a framework that accounts for the behavior of spacetime on both infinite and subatomic scales. A theory like this could potentially offer insights into the nature of singularities and how the universe truly works. One approach to resolving the issue of singularities is the theory of loop quantum gravity. This theory proposes that at microscopic scales, spacetime is quantized, meaning it consists of discrete, inseparable units. These fundamental units are often referred to as loops or spin networks. In loop quantum gravity, the concept of quantization is applied to spacetime itself. This means that spacetime isn't considered a continuous and infinitely divisible entity but rather a collection of discrete components. These discrete units of spacetime are often viewed as interconnected loops or networks that represent the underlying structure of the fabric of the universe. Within the framework of loop quantum gravity, singularities associated with dark openings and the Big Bang could be resolved. One of the key insights of this theory is that at microscopic scales, the discrete nature of spacetime prevents the occurrence of infinite densities and curvatures that result in singularities in classical general relativity. For example, with regard to dark openings, loop quantum gravity suggests that as matter falls toward the core, the spacetime fabric becomes increasingly discrete. This discreteness prevents the matter from reaching an infinitely dense peculiarity. Instead, the collapsing matter experiences a quantum bounce near the core, where it rebounds and begins to expand again. This scenario leads to the formation of a new spacetime region inside the dark opening, often referred to as a quantum dark opening or a bounce region. Heavenly dark openings are the most commonly observed type of dark opening in the universe. They are formed through gravitational collapse at the end of a massive star's life. Once a massive star exhausts all its nuclear fuel, the outward pressure generated by nuclear reactions can no longer counteract the force of gravity pulling inward. The gravitational force becomes dominant, causing the star to collapse under its own weight. This collapse results in the formation of a heavenly dark opening. As the star collapses, it becomes incredibly compact, packing a lot of mass into a very small volume. As a result, heavenly dark openings typically have a mass ranging from a few times to many times that of the Sun. Despite their mass, they have very small sizes. Their diameter is a few kilometers, which demonstrates how incredibly dense they are. The enormous density of a heavenly dark opening leads to the formation of an event horizon, a boundary beyond which nothing, not even light, can escape. This event horizon marks the point of no return, where the gravitational pull of the dark opening becomes so strong that any object or information that crosses it is trapped forever inside the dark opening. Then we've got intermediate mass dark openings. While the exact mass range for intermediate mass dark openings is still something researchers need to put through more examination and refinement, they are generally thought to have masses ranging from thousands to hundreds of thousands of times that of the Sun. These massive entities occupy the central regions of most galaxies, including our own Milky Way. They hold significant gravitational influence over their cosmic surroundings and have a substantial impact on the formation of galaxies. The formation of supermassive dark openings remains an area of research and is still not fully understood. Nevertheless, various theories have been proposed to explain their origins. One prominent hypothesis suggests that supermassive dark openings grow from smaller dark openings through a process called accretion. According to this idea, as matter, such as gas, dust, and stars, accumulates around a dark opening, it forms a swirling disk known as an accretion disk. The dark opening's immense gravitational force draws material from this disk, causing it to spiral inward and eventually merge with the dark opening. Over vast time frames, this continuous accumulation of matter allows the dark opening to grow to a supermassive scale. During the accretion process, enormous amounts of gravitational potential energy are released as the matter falls into the dark opening. This released energy powers some of the brightest and most powerful phenomena in the universe. However, away from that, there are charged dark openings, which represent a fascinating variety of dark openings characterized by the presence of an electric charge. There are two main types of charged dark openings: Reissner-Nordström dark openings and Kerr-Newman dark openings. Each type exhibits distinct properties that are formed from the interaction between the dark opening's charge and other factors such as spin. Reissner-Nordström dark openings are charged but non-rotating. They are described by the Reissner-Nordström solution within the framework of general relativity. The charge of these dark openings affects the behavior of their gravitational field. However, in terms of their overall structure, Reissner-Nordström dark openings are similar to uncharged dark openings. They have an event horizon, but the size of the event horizon for a Reissner-Nordström dark opening depends on both its mass and electric charge. On the other hand, Kerr-Newman dark openings are charged and rotating. They are characterized by the Kerr-Newman solution in general relativity. The combination of electric charge and rotation introduces unique phenomena associated with these dark openings. One of the notable effects is called frame dragging, which occurs because the rotating dark opening drags and twists the surrounding spacetime curvature. Kerr-Newman dark openings have both an event horizon and an inner region known as the ergosphere. The ergosphere is a region around the dark opening where the effects of frame dragging are so strong that objects within it are forced to move in the same direction as the dark opening's rotation. The presence of charge in dark openings introduces an additional layer of complexity to their behavior and interactions. Charged dark openings possess an electric field that extends beyond the event horizon. This electric field can influence the behavior of nearby particles and other objects. Furthermore, the electric charge of a dark opening contributes to its overall energy. This, in turn, can affect the dynamics of its interactions with surrounding matter and radiation. As we continue to study the properties of charged dark openings, we gain deeper insights into the interplay between electric charge, gravitational forces, and the fundamental nature of these captivating cosmic objects. Now, talking about radiation, one of the key concepts related to dark openings is Hawking radiation, proposed by physicist Stephen Hawking. According to this theory, dark openings are not entirely black but emit radiation due to quantum effects near the event horizon. This process involves particle-antiparticle pairs spontaneously forming near the event horizon. One particle escapes as radiation, while the other falls into the dark opening. Over time, this emission of radiation leads to a gradual loss of mass and energy for the dark opening.